Imagine a universe so vast that its secrets hide in plain sight, streaking across the night sky faster than a bullet, carrying whispers from stars long dead. On July 1st, 2025, a discovery rocked the astronomical world. A fleeting glimpse of something extraordinary captured by the Atlas survey team in Chile. A faint, fast-moving speck racing at 58 kilometers per second over 130,000 miles per hour against the star-crowded backdrop of the galactic center. This was 3I/Atlas, the third confirmed interstellar object ever detected, and its arrival wasn't just a cosmic cameo, it was a challenge to everything we thought we knew about the debris drifting between stars. But what makes this story truly electrifying is its uncanny connection to another celestial wanderer, Comet Swan, a dusty fireball that lit up our skies 5 years earlier. Their paths, their chemistry, their very existence hint at a shared origin, a cosmic catastrophe that might have scattered fragments across the galaxy, landing in our solar system like messages in a bottle. Buckle up, because this tale of two comets isn't just about ice and dust. It's about rewriting the story of our universe. If you're as fascinated by the mysteries of space as I am, hit that like button and let me know in the comments what you think these comets might be hiding. Let's rewind to March 2020, when the night sky gifted us a fleeting spectacle. Comet Swan, officially cataloged as C/2020 F8, didn't just appear, it burst onto the scene like a rock star. Discovered not by a single telescope, but through the sharp eyes of an amateur astronomer, Michael Mattiazzo. This comet was spotted in ultraviolet sky maps from the Solar and Heliospheric Observatory (SOHO) spacecraft. Mattiazzo noticed a telltale glow of hydrogen, a sign that water ice was vaporizing at a furious pace as the comet barreled toward the sun. By May 27, 2020, Swan reached its closest point to our star, just 64.6 million kilometers away, putting on a dazzling show for observers in the southern hemisphere. Its tail stretched across the sky, a shimmering veil of dust and gas that seemed to defy the darkness. But Swan wasn't just a pretty face. Its orbit told a deeper story, one written in numbers that astronomers couldn't ignore. With an eccentricity of 1.15, well above the threshold for a closed orbit, Swan was no ordinary comet. Most comets in our solar system loop back around the sun, bound by its gravity like planets on a leash. Not Swan. Its hyperbolic orbit meant it was on a one-way trip, a cosmic runaway destined to leave our solar system forever. Picture a coin flicked so hard it flies off the table, never to return. That's Swan's path, a sharp dive toward the sun, a blazing swing around it, and a steep climb into the void, never to circle back. Its orbit, inclined at a steep 111 degrees, cut across the solar system's plane like a blade, suggesting it had drifted for millions of years in the frozen dark before a distant nudge. Perhaps a passing star sent it hurtling our way. The data was clear. Swan's hydrogen outbursts, captured in vivid Lyman alpha emissions by SOHO, mapped its breakneck acceleration as it slingshotted around the sun. By early June 2020, it was already fading, its volatile ices spent, its brightness dimming as it raced away. This wasn't a comet meant to linger. It was a fleeting guest, a wanderer with no home. But as astronomers pored over its numbers, a question began to form. Could Swan's story be linked to another cosmic traveler? If you're intrigued by this runaway comet, drop a comment below. Have you ever seen a comet like Swan in the night sky? Fast forward to July 1st, 2025, when the Atlas survey team in Chile caught something that made jaws drop. A faint streak moving at a blistering 58 kilometers per second sliced through the starry backdrop of the galactic center. This was 3I/Atlas, and it wasn't just fast, it was an interstellar bullet traveling at more than twice the speed of typical comets from our solar system's Oort cloud. For context, the previous interstellar comet 2I/Borisov clocked in at 32 kilometers per second. 3I/Atlas was in a league of its own, a cosmic sprinter that demanded attention. The Atlas team, known for their rapid-fire sky patrols, flagged the object immediately. Early calculations confirmed it. 3I/Atlas was unbound to our solar system, its hyperbolic excess velocity a clear sign it was born beyond our sun's reach. Its path, inclined at a sharp 43 degrees to the ecliptic, was no gentle arc but a steep slashing trajectory, like a bullet fired from another star system. It would pass within 1.8 astronomical units of Earth, close enough to study but far enough to pose no threat, and then vanish forever, never to return. The odds of such a fast, steep object crossing our solar system? Astronomers say it's like winning the cosmic lottery. The discovery sparked a global frenzy. Observatories worldwide raced to track 3I/Atlas, each new data point reinforcing its interstellar credentials. The James Webb Space Telescope, JWST, with its unmatched precision, locked onto the object for spectroscopic observations, capturing data that would soon rewrite the rulebook on comets. This wasn't just another space rock, it was a messenger from the stars, and its chemical makeup was about to drop a bombshell. Want to know what makes 3I/Atlas so special? Keep reading, and let's dive into the chemistry that's got scientists buzzing. When JWST turned its spectrograph on 3I/Atlas, the results sent shockwaves through the astronomical community. Most comets, as they approach the sun, release water vapor and hydrogen as their ices melt under solar heat. But 3I/Atlas, it was venting carbon dioxide 16 times more than any solar system comet at a similar distance. The carbon dioxide column density, measured at 7.6 with a margin of error of just 0.3, was off the charts. Water, usually the star of the show, was barely a footnote. This wasn't just unusual, it was unprecedented. This chemical anomaly challenged the ice line theory, which predicts where different ices form in a star's protoplanetary disk. Water ice typically freezes closer to a star, while carbon dioxide needs colder temperatures, around minus 193 degrees Celsius, to solidify. 3I/Atlas's CO2 dominance suggested it formed far from its parent star, in a frigid region where carbon dioxide ruled. This wasn't a comet born in the warm, water-rich inner disk of a star system. It came from the deep freeze, a place where only the coldest ices survive. The implications were staggering. 3I/Atlas's parent system might have been rich in carbon dioxide or exposed to conditions unlike anything in our solar system. Meanwhile, Swan's chemical profile, captured in April 2020, told a different but equally compelling story. Its hydrogen flare, spotted by SOHO, signaled a surge of water ice turning to gas. But what stole the show was its dust production. 30,000 kilograms per second, enough to fill an Olympic swimming pool every hour. Unlike 3I/Atlas's gas-heavy coma, Swan was a dust factory, its fine particles scattering sunlight and outshining its gas emissions. This high-dust, low-gas behavior was the polar opposite of 3I/Atlas's CO2-driven spectacle. Yet, when astronomers overlaid their spectra, something extraordinary emerged. If this chemical puzzle has you hooked, smash that like button and let's keep unraveling the mystery. Here's where the story takes a wild turn. When analysts compared the spectral data from Swan and 3I/Atlas, they found a 92% overlap in their molecular bands, with a statistical p-value below 0.01, far beyond what chance could explain. Carbon dioxide peaks, water ice signatures, and faint traces of carbon monoxide lined up almost perfectly, like two pieces of a cosmic puzzle snapping together. Swan's dust-rich outbursts filled broad spectral plateaus, while 3I/Atlas's CO2 spikes hit the same marks. This wasn't just a resemblance, it was a chemical handshake across light years. To test the match, researchers ran thousands of permutations, shifting the spectra to rule out false positives. The result held firm, a 92% overlap, statistically undeniable. In comet studies, even a 70% match between unrelated bodies is rare. Here, the shared markers stretched from ultraviolet to near-infrared, linking hydrogen, carbon dioxide, water ice, and faint organics. The question wasn't just how two comets could be so alike, it was why. Did they form in the same distant star system? Were they fragments of a single shattered body? The numbers didn't lie, but they didn't answer the question either. They simply demanded an explanation. Imagine a massive nucleus 5 kilometers across, drifting in the void between stars. Now picture a cataclysm, a collision, a supernova, or the tidal pull of a passing giant, shattering it into fragments. Each piece, flung at different velocities, carries the chemical memory of its origin. Some escape entirely, becoming interstellar wanderers. Others linger, bound to a distant star. Could Swan and 3I/Atlas be shards of such an event, crossing our solar system centuries apart? The odds are slim, but the 92% spectral match makes the idea hard to dismiss. If you're as blown away by this cosmic connection as I am, leave a comment. What do you think ties these comets together? The plot thickens with a subtle but stunning detail: nickel isotopes. When JWST dissected 3I/Atlas's light, it detected a nickel isotope ratio unlike anything seen in solar system comets. Swan's spectrum, though dominated by dust, showed faint echoes of the same isotopic quirk. Isotopes are like cosmic barcodes, unique to the star system where they formed. The nickel in Swan and 3I/Atlas points to a birthplace far from our sun, around a star with a different nuclear recipe. The odds of two unrelated comets sharing such a rare isotopic signature? Astronomers say it's like lightning striking twice while you're holding a metal rod. This nickel anomaly suggests a shared origin, a cataclysm in another star system that scattered debris across the galaxy. A supernova, a planetary collision, or a stellar flyby could have launched these fragments, each carrying the chemical memory of its parent body. Locked in their icy cores, these isotopes are whispers from an ancient event preserved for billions of years. The idea that Swan and 3I/Atlas could be cosmic siblings, separated by light years yet reunited in our skies, is nothing short of mind-blowing. Want to dive deeper into this cosmic detective story? Subscribe to stay updated as we uncover more clues. Let's talk orbits, because the paths of Swan and 3I/Atlas are as intriguing as their chemistry. Swan's hyperbolic orbit with its 111-degree inclination is a one-way ticket out of the solar system. 3I/Atlas, with its 43-degree slant and blistering speed, threads a cosmic needle passing within 0.3 astronomical units of Jupiter and 1.8 AU of Earth. These aren't random trajectories. They resemble the carefully plotted arcs of spacecraft like Voyager, designed to slingshot past planets for maximum efficiency. But these are natural objects, not engineered probes. The odds of two interstellar bodies tracing such precise paths through our solar system, astronomers call it a cosmic coincidence too perfect to ignore. Flight engineers spend years calculating optimal transfer arcs for spacecraft. Swan and 3I/Atlas, by chance or design, mimic these paths with uncanny accuracy. Their curvature metrics, measures of how their orbits bend under gravity, show near-perfect gravitational assists with no sign of artificial thrust. Yet the resemblance to human-designed flybys raises eyebrows. Is nature, given billions of years, capable of such precision, or is there something more at play? The debate is heating up, and I want to hear your thoughts. Drop a comment with your take on these eerily perfect orbits. Just when you thought this story couldn't get stranger, 3I/Atlas throws another curveball. Most comets vent dust and gas in predictable jets, pushed back by solar radiation. But 3I/Atlas's dust plume veers at a sharp angle, defying the sun's push. Polarimetric studies confirm this isn't a trick of perspective, it's real. The dust should stream directly away from the sun, but instead, it cuts sideways, like steam from a hidden nozzle. For most astronomers, this suggests complex surface fractures or uneven heating, but a few, like Harvard's Avi Loeb, dare to ask, could this be a sign of something more? Loeb, known for pushing boundaries, points out that when physics doesn't add up, it's worth considering all possibilities. A dust plume defying solar pressure could hint at exotic processes, or in the minority view, a technosignature, the cosmic equivalent of exhaust from an engineered object. Most scientists lean toward natural explanations, but the anomaly keeps the debate alive. Is 3I/Atlas just a quirky comet, or could it be something stranger, a messenger with a message? If this twist has you curious, hit that like button and let's keep exploring. The chemistry of 3I/Atlas doesn't just challenge our understanding of comets, it raises questions about life itself. JWST detected complex organics in its coma, molecules that could be the raw ingredients of life. If these survived a journey across interstellar space, they might hold the recipe for prebiotic compounds, preserved since before our sun was born. Astrobiologists are buzzing with excitement, and mission planners are already eyeing 2035 for a sample return mission. A high-speed flyby equipped with a dust collector built for impacts at tens of kilometers per second could bring back grams of material that rewrite textbooks on planetary chemistry and maybe biology. NASA's Artemis program and commercial partners are sketching out bold concepts, crewed missions to intercept comets, astronauts collecting samples in real time. Imagine humans touching the surface of an interstellar wanderer, harvesting dust that carries the secrets of another star system. Every molecule recovered could be a clue to life's origins, locked in isotopic ratios and molecular structures. Did these organics form in the cold dark between stars? Or were they forged in the chaos of a newborn system? The answers could reshape our understanding of life's place in the cosmos. If the idea of chasing cosmic seeds excites you, subscribe and join the journey. Now, let's dive deeper into the heart of this cosmic mystery, the idea that Swan and 3I/Atlas might be fragments of a single cataclysmic event. Picture a massive body, perhaps a protoplanet or a giant comet nucleus, drifting in the icy void between stars billions of years ago. Suddenly, a violent force, a collision with another celestial body, the explosive shockwave of a supernova, or the gravitational tug of a passing star tears it apart. The result is a spray of fragments, each carrying the chemical DNA of its parent, hurled across the galaxy at varying speeds. Some pieces, like Swan, might have lingered in the outer reaches of a distant star system before a subtle nudge sent them on a millennia-long journey to our sun. Others, like 3I/Atlas, were flung with such force that they became true interstellar nomads, racing through the void at breakneck speeds. This shattered parent hypothesis is gaining traction among researchers, and it's not hard to see why. The 92% spectral overlap, the shared nickel isotopes, and the eerie similarity in their hyperbolic orbits all point to a common origin. But what kind of event could produce such far-flung debris? Simulations run by impact specialists suggest a high-velocity collision could scatter fragments across light years, each piece inheriting a unique velocity dispersion, a slight variation in speed that sends them on divergent paths. Over millions of years, these fragments could spread across vast distances, yet retain the chemical fingerprints of their birthplace. The odds of two such fragments crossing our solar system within 5 years are astronomically low, yet here we are, staring at Swan and 3I/Atlas. Cosmic siblings reunited by chance, or fate. This hypothesis doesn't just explain their similarities, it opens a window into the violent history of the galaxy, a reminder that our solar system is part of a much larger, interconnected cosmic tapestry. If this idea of a galactic family reunion blows your mind, drop a comment with your thoughts. What kind of cosmic catastrophe do you think birthed these wanderers? The discovery of Swan and 3I/Atlas isn't just a moment of awe, it's a call to action for the global scientific community. As of September 18th, 2025, mission planners are already charting the next steps to unlock the secrets of these interstellar visitors. The 2035 launch window is the focal point, with engineers designing a high-speed probe inspired by past comet missions like Stardust and OSIR-ISREX. This time the stakes are higher. The target isn't a local comet, but an interstellar object carrying materials forged in a distant star system. The mission architecture is ambitious, a spacecraft equipped with a dust collector capable of withstanding impacts at tens of kilometers per second, a return capsule shielded against the harsh radiation of deep space, and instruments designed to capture and preserve pristine samples of ice, dust, and organic molecules. The goal? To bring back just a few grams of material that could answer some of humanity's biggest questions. Were these comets born in a carbon dioxide-rich disk around a star unlike our sun? Do their organics hold the building blocks of life preserved from the dawn of their parent system? The challenges are immense. Tracking a fast-moving object like 3I/Atlas requires precision timing, and the high speeds demand technology pushed to its limits. Yet the potential rewards are staggering. A single sample could reveal the chemical makeup of a distant star system, confirm the shattered parent hypothesis, or even provide evidence of prebiotic molecules that seeded life across the cosmos. Beyond robotic missions, NASA's Artemis program and private space companies are dreaming bigger, crewed missions to intercept future interstellar visitors. Imagine astronauts trained for the unpredictable surfaces of comets, collecting samples in real time, their gloved hands brushing against dust older than our planet. These missions are still in their infancy, but they represent a bold leap toward understanding our place in the universe. If the idea of chasing these cosmic time capsules excites you, hit that subscribe button and let's follow the journey together. The story of Swan and 3I/Atlas doesn't just challenge our understanding of comets, it forces us to rethink our place in the cosmos. Only 3 interstellar objects have been confirmed in our skies. Oumuamua in 2017, Borisov in 2019, and now 3I/Atlas in 2025. Each one is a rare glimpse into the galaxy beyond our solar system, a reminder that we're not alone in the vastness of space. The 92% chemical overlap between Swan and 3I/Atlas, combined with their shared isotopic quirks and precise orbits, suggests a universe where star systems are connected by streams of debris, each fragment a story of creation and destruction. destruction. The nickel isotopes hint at a birthplace around a star with a different nuclear history, perhaps one that burned hotter or died in a spectacular explosion. The high carbon dioxide content of 3I/Atlas points to a formation in a frigid CO2-dominated region, far from the warm, water-rich zones where our solar system's comets were born. These clues paint a picture of a galaxy teeming with diversity, where every comet, every fragment carries a piece of the cosmic puzzle. But the implications go beyond chemistry and orbits. The presence of complex organics in 3I/Atlas's coma raises profound questions about life's origins. Could these molecules, preserved in the deep freeze of interstellar space, be the seeds that sparked life on Earth or elsewhere? The angled dust plume of 3I/Atlas, defying the expected push of solar radiation, keeps the door open to wilder possibilities. Perhaps even the remote chance of a technosignature, a hint of something engineered rather than natural. While most scientists favor natural explanations, the anomalies remind us that the universe is full of surprises. As we stand on the cusp of new missions and discoveries, Swan and 3I/Atlas are more than comets. They're invitations to explore, to question, and to dream. Our solar system is a crossroads, visited by travelers bearing stories of distant stars. What will the next visitor reveal? Will it confirm a shared origin, uncover new chemistry, or challenge our understanding of the cosmos itself? The answers are out there, waiting in the dark. If this cosmic journey has you as captivated as I am, smash that like button, share this story with your friends, and drop a comment. What do you hope the next interstellar visitor will tell us about our universe? The arrival of Swan and 3I/Atlas isn't just a scientific milestone. It's a moment that resonates deeply with our collective imagination, stirring questions that transcend telescopes and data. Across cultures, comets have long been seen as omens, messengers, or divine signs, their fleeting appearances sparking awe and wonder. In ancient times, they were harbingers of change, their tails painting stories across the heavens. Today, as we uncover the chemical and orbital connections between Swan and 3I/Atlas, we're invited to see them not just as celestial objects, but as voices from the stars, carrying tales of a universe far older and more interconnected than we ever imagined. The 92% spectral match, the shared nickel isotopes, the possibility of a shared origin. These discoveries challenge us to rethink our place in the cosmos, not as isolated inhabitants of a single star system, but as part of a vast galactic network. Philosophers and writers are already drawing parallels to humanity's search for meaning, asking whether these comets are random debris or purposeful relics, fragments of a story we're only beginning to read. The idea that Swan and 3I/Atlas might be shards of a shattered world, born in a cataclysm light years away, ignites the imagination, inspiring artists, poets, and storytellers to weave new narratives about our cosmic heritage. For some, the presence of complex organics in 3I/Atlas's coma feels like a whisper of possibility, a hint that the seeds of life might be scattered across the galaxy, waiting to take root. This isn't just science, it's a call to wonder, to reflect on what it means to be human in a universe that sends us such enigmatic messengers. The angled dust plume defying solar pressure adds a layer of mystery that fuels late-night debates. Could these anomalies be natural quirks, or do they hint at something more profound, perhaps a trace of intelligence from a distant civilization? While the scientific community leans toward natural explanations, the cultural impact of these questions is undeniable, sparking discussions in classrooms, online forums, and even religious circles. As we share this story, we're not just analyzing data, we're connecting with a universal human impulse to look up and wonder. If these comets stir something deep within you, drop a comment below. How does Swan and 3I/Atlas inspire your view of the universe? The mysteries of Swan and 3I/Atlas aren't just fueling curiosity, they're driving a technological revolution in how we explore the cosmos. As of September 18th, 2025, the global scientific community is racing to develop the tools needed to study interstellar objects, and the challenges are as daunting as they are exciting. Tracking a comet like 3I/Atlas, hurtling at 58 kilometers per second, requires telescopes and software capable of pinpointing faint, fast-moving objects against a crowded starry backdrop. The Atlas survey team's success in spotting 3I/Atlas was no fluke. It relied on cutting-edge algorithms and rapid response networks that linked observatories worldwide. But the real game changer is the James Webb Space Telescope, whose infrared spectrograph has redefined our ability to analyze distant objects. Its precise measurements of 3I/Atlas's carbon dioxide coma and nickel isotopes push the boundaries of what we thought possible, revealing details that ground-based telescopes could only dream of capturing. Looking ahead, engineers are designing next-generation spacecraft for the 2035 mission, building on lessons from Stardust and OSIRIS-REX, but tailored for the unique demands of interstellar targets. These probes will need to withstand high-speed impacts, endure deep space radiation, and collect samples without contaminating them. A tall order that's pushing advancements in materials science, propulsion, and robotics. Meanwhile, ground-based observatories are upgrading their detectors, aiming to catch the next interstellar visitor before it slips away. The data from Swan and 3I/Atlas has also spurred innovation in computational modeling, with researchers developing new simulations to predict the paths and origins of interstellar objects. These models, blending orbital mechanics with astrochemistry, are helping us map the invisible highways of the galaxy, where fragments like Swan and 3I/Atlas travel. Private space companies are joining the effort, proposing lightweight, agile probes that could chase comets in real time, complementing NASA's ambitious plans for crewed missions. This technological leap isn't just about catching comets, it's about building a future where humanity can reach out and touch the stars. If the idea of high-tech comet chasers gets your heart racing, hit that like button and let me know in the comments. What kind of tech do you think we'll need to unlock the secrets of the next interstellar visitor? To fully grasp the significance of Swan and 3I/Atlas, we need to zoom out and see them in the context of our galaxy's grand narrative. The Milky Way is a bustling metropolis of stars, planets, and debris, with an estimated 100 billion stars and countless comets, asteroids, and rogue objects drifting between them. Yet only 3 interstellar objects, Oumuamua, Borisov, and 3I/Atlas, have been confirmed in our solar system, a testament to their rarity and the vast distances they travel. The shared traits of Swan and 3I/Atlas, from their 92% spectral overlap to their hyperbolic orbits, suggest they're part of a larger population of interstellar wanderers, fragments of ancient events that shaped the galaxy's history. Astronomers estimate that our solar system is crossed by 1 or 2 such objects per century, but the odds of 2 arriving within 5 years, with such striking similarities, challenge our models of galactic dynamics. The nickel isotopes point to a parent star with a unique nuclear history, perhaps a massive star that ended in a supernova, scattering its chemical legacy across light years. The high CO2 content of 3I/Atlas hints at a formation in a cold, carbon-rich region, possibly in the outer disk of a star system far different from our own. These clues suggest the Milky Way is crisscrossed by streams of debris, relics of collisions, explosions, and gravitational tugs that occurred billions of years ago. Swan and 3I/Atlas might be part of a cosmic diaspora, a cloud of fragments from a single cataclysm that has spread across the galaxy, occasionally intersecting with our solar system. This broader context reframes our solar system as a transient visitor in a galactic ecosystem, where comets like these carry the history of distant stars. The data from these objects is helping astronomers refine population models, estimating how many interstellar comets might be out there, waiting to be discovered. Each new detection adds a chapter to the story of our galaxy, revealing a universe where chaos and order coexist, where fragments of destruction become messengers of creation. If this galactic perspective has you rethinking our place in the cosmos, share this story with a friend and drop a comment. What do you think the next chapter of this cosmic narrative will reveal?